friends, in this lesson we will take a quick look at why array indexes are 0-based instead of 1. Because this is a major reason of confusion among novice programmers. I still remember myself being a beginner student and seeing array indexes being 0-based and wondering, wow, that's just so wrong. Why aren't they 1-based? That's what we are all used to in our daily lives. But of course, once I understood the reason behind it, I realized that it is much more efficient to have them starting at 0. Before we begin, I should point out that this is not a mandatory concept to learn, and it is based on a lot of things that I haven't spoke about yet, and it's rather advanced. So, if you don't understand all of it, it is fine. You can come back and watch this video again at a later time when you will be more advanced. The first thing we need to remember in order to understand the concepts described in this video is reference types. I was explaining in a previous video that reference types are just addresses stored in the stack memory that point to objects located on the heap memory. Well, this is a high-level language implementation of a much older concept coming from lower-level languages such as C and C++, namely a pointer. A pointer is conceptually the same thing as a reference in C#, with a few major differences. First of all, references point to an object in memory, while pointers are not type-safe. You cannot guarantee the correctness of the memory they point at. Take a look at the following code. This is how we declare a C++ style raw pointer in C#, and because we are dealing with stuff that can be very harmful to our programs, we need to wrap it inside an unsafe block of code. We also need to go to the properties page of our project, and in the build section, check the Allow Unsafe Code option. Anyway, back to our code, this int pointer is not guaranteed to actually point to an int. It could point to a char, double, or just random memory. On the other hand, when we have a code like this, you can recognize it as a reference. I have already previously said that strings are primitive types that are references. So, while you might consider a reference doing same stuff as a pointer, namely store an address on stack that points to something on heap, references do not point to just a place in memory. They point to an object that lives someplace in memory. Objects have the property that they can be moved around in memory, and they are what programmers call type-safe, in the sense that a string reference has just one of two states. It points to no object on the heap and is therefore null, or it points to a valid string object. This is unlike a pointer, which points to a location that can contain nothing or anything. Another difference between the two concepts is that reference types are managed by a construct called garbage collector, which automatically does the memory heavy lifting for us. Things like allocating memory, cleaning objects that are no longer used from memory, etc. With pointers, we have to do all that manually, and failing to do so in a correct way can have horrible results such as crashing our program. So, it's a nice thing for C# to do all that complicated and dangerous stuff for us automatically. This is also the reason why I have to surround my pointer declaration with an unsafe block of code, because I am taking control away from the garbage collector and I'm switching everything to manual command. Now, take a look at this code. I have a normal C# array, and in this unsafe block of code, I am using a fixed block of code which basically tells the compiler, hey, do not allow garbage collector anywhere near here, do not move my array in memory, leave it fixed or pinned to the memory location where it was declared. Now, the syntax you're seeing here comes from C++. I have a variable called p, and p is a pointer to my array. What we already know is that C# arrays are objects. We have goodies such as the length property that we can use on them, like we did in the previous lessons, and they have bounds checking, meaning we will get exceptions when trying to access indexes that are out of the range of valid indexes, and so on and so on. C++ arrays are not like that. They are not objects, they are simply names to memory addresses. Now, let me quickly draw the graphical representation of my array in memory. These are the array elements, and my p variable is a pointer, which I said it is an address, and that address points to the location of the first byte of the first element in my array. Of course, we know ints require 4 bytes of memory, so I can draw them too. 1, 2, 3, and 4 bytes for the 8, and another 4 bytes for the 4, and 4 bytes for the 0, and so on, and so forth. Each array cell in here requires 4 bytes of memory because they store ints. If I want to have a look at the value of the first element in my array, I need this special *p syntax, which is also a C and C++ thing called dereference, which translates to go to the address that the p pointer references and give me the value stored there. Do not confuse the two stars. The star here means p is a pointer variable, while the star here means the dereferencing the value stored at the memory address that the p variable points at. If I run the program now, we will see that we get a value of 8, because that's the value at the first cell of our array, and the p pointer variable points to the address of this first element. Another crucial difference between C# references and C++ pointers is that we can actually do arithmetic with pointers. If I put a parenthesis and say, hey pointer, go to p plus 1, well, the plus 1 part here means what data type p is pointing at 1 times the size of that data type. Well, p is pointing at ints, and 1 times the size of an int equals 4, which means that p plus 1 will not be this byte right here. The second byte of the first cell, it would be 1 times the size of an int, 4 bytes, which would result in p pointing now to this byte. Of course, this byte is the first byte of the second element in our array, and we can check this at the console. P plus 2 will be the third element in our array, because p plus 2 times 4 bytes of an int means 8 bytes in, and so on and so forth. Well, what if I want to still use this plus arithmetic but still point to the first byte of the first array cell so that I can access its value? What would I add? Obvious enough, I have to add 0, the magical 0, which is the base of our array indexers. This concludes to p being a pointer to the first address in my array, and if I don't want to offset into my array at all, it will have to be p plus 0. Or in a syntax that you're already familiar with, let's go to the first address of my array and offset from that location with a value of 0. The first element in my array is 8, and if I offset it with 0, it's still going to be 8. And this is the reason why arrays are 0-based, because it all has to do with memory addresses in RAM. Of course, my array being an object means that it stores some extra info in there, such as its length, its type pointer, and other stuff, and that means that in reality, the value 8 does not really physically start at the beginning of the array, but C# is smart enough to give us the location of the first array cell when we try to access it. For those of you that are satisfied with this explanation, the lesson ends here. For those who want to see it in action at an even lower level, stick around while we dive into the world of assembly code and memory locations and bytes. If I hit my F11 key to go into debug mode, I can open several advanced debug windows such as the registers, which are basically little pieces of memory that sit on the CPU memory, where we can see our RAM, and disassembly, where we can see our C# code being translated into these native CPU instructions. If I F10 to this move instruction, we will see that this is the memory location in RAM of my array. And if we go to that memory address, we can actually see that value stored here. From here on, downwards, it's where my array lives inside RAM. We don't see the values yet because this instruction, assigning them, hasn't run yet. But we can already see that the length of the array is 6 because we declared it with 6 elements, and this first location is called a type pointer, which tells the compiler the type of values that this array stores, in our case ints. The actual values of my array starts at this location downwards, while in C++ they would contain the name of the array at the first memory location, and the values would start immediately after, since C++ arrays don't store extra information such as the length and all as the C# arrays do. As I step through these native instructions, we get to see the data we put in my array field the RAM addresses, and would you look at that? We have 840822. Well, the values I've put in the initialization of my array were 840822, which means that our actual data begins right here. If I continue to step through, I will get to this instruction, load effective address, EAX plus 8. Well, the plus 8 is just so we get past these 8 bytes right at the beginning of the array where the extra info is located. And this is where the pointer will point it, the beginning of our data at this RAM memory address. I can even draw it to you. Our P pointer right here points to this address, and you have to be careful to brand this into your head. This is the address, this is the value. Again, this is the address, this is the value at that address. If I were to have P plus 1, I would have to go 1 times the size of an int, 4 bytes, and I would end up here at the address of this second array cell, which has a value of 4. P plus 2 would be this address because 2 times the size of an int means 8 bytes offset, which gets us to the address of this third cell, which has a value of 0, and so on. I know that we should have the values on the right here, but that has to do with endian swapping, which is a different topic for another time. Anyways, there you have it, that's why arrays are zero-based. In the next lesson, we will learn about functions or methods, as they are called in C#. For now, goodbye.